Okay. So this slide gives you idea. Okay, till around 2023, even the 256 qubit processors were available. We didn't have any guarantee on the number of logical qubits. Okay. So the processor were there, but the performance was very erratic, and with that time's availability of error correction codes running on top of them, you could not guarantee any logical qubit. Come to 2024, now with a 256 qubit processor, there is a kind of guarantee that you can get approximately 10 qubits, logical qubits operations. Okay, that means now it is almost for 20 qubits are mapping into one. So like there I showed one qubit connecting to four, say 5 qubit representing one. Here it is actually becoming 20 qubits. Okay. Once they move to the third generation, where you have a designs of approximately 1000 qubits, but the logical qubit you are getting out of just 30 qubits. So as you see, it's not a linear increase. That I increased it by 4 times, okay, approximately, but my number of qubit has only risen by 3 times. Okay. So it is telling me, because of the complexity of the interconnects, once you make a more and more complex quantum processors, the number of logical qubits which are going to come up may not be linear. You may be sublinear or suboptimal from there. Okay. The expectation is by next year, you should have designs available somewhere around 10K or 5K kind of a thing, and you should be touch about 100 logical qubits. Okay. The way the present problem statements are, if we are able to touch 100 logical qubits available, doing a largely error-free operation, that is where the quantum systems will become mainstream. That's the time when they will start solving problems of today, which we are not able to solve, or which the quantum supercomputers cannot handle. Below this, supercomputers are solving it much better. So that's why people don't find it as it's a promising technology, but it's not being used at scale. But this is the promise. If we are able to reach somewhere here, we should be able to have a quantum computers start coming mainstreams. Okay. Now to do this quantum fault tolerance, there are different technologies of codes, surface codes, Stein code. These are the technologies which are, or the error correction codes which are there, multiple. And if you want to have an intuitive understanding of error corrections, so all those who have studied digital communication, we have a series of LDPC codes or the other codes which are there. Similar kind of systems or the error corrections are coming into this. Even LDPC is one of the technology even in being implemented on the quantum error corrections, but that is much, much lower. Now we have a much more advanced quantum error correction codes. Okay. So that's technologically where we are. Hopefully by next year, we should, somebody should be able to reach this, probably if not next, probably 2027, a 100 qubit processor, which is logical 100 qubits and largely error-free. Next. Okay. So now we understand, okay, even a 50 qubit processors can't do everything, but just to get an idea, some numbers in our mind, okay, what a 50 qubit quantum processor or quantum computer can do. Okay. So it can represent in the 50 qubit system, its superposition state, it can represent 2 to the power 50 states. Okay. It's a approximately, I will say, complex amplitude for a vector. This will require approximately 18 petabytes of RAM. Okay. And this much is not feasible to do it with the present Indian or present global supercomputer technology also. Okay. So these are the few numbers which you can keep in mind. But as we discussed, this tutorial, you cannot process this information. This is a theoretical promise, as I show in the block sphere. This is a theoretical promise of that information, okay, and their interaction. But classically, we are not able to reach there, okay. But still, the quantum advantage will arrive once we are able to extract sufficient processing power through this And once we are able to resolve this, some of these limitations which are there. So there are limitations in the time of computation time, the gate fidelity, the performance, the overall error correction. Okay. Also, the quantum speed up presently is observed into certain class of problems, not all problems. Okay, that thing will be covered later by my team in the probably the third day or fourth day. Like which are the problems which are solved effectively by this. So optimization class of problem, are all the problems are suited optimization? No. So there are convex, non-convex optimizations. So a particular set of that can be effectively solved by this. Okay. So that's where the 50 qubit kind of a computer represent this kind of information. Okay, next. So present systems, both Google Willow and IBM Heron, they have a low quantum value and imperfect gate fidelity of 99.5, touching 99.9. Okay, and brief coherence time of microseconds. So that why the coherence times becomes important, as I discussed, that as we process the information from input space to output, if the qubit starts from this multiple gates, if it decoheres in between, the information is lost. So you need to, the qubit need to stay coherent for that complete gate operation. Okay, and if you have a few microseconds of survival, and I can do only 15K operations per second, okay, as I told earlier, so that limits how many operations I can do within that small amount of time. So these are again the limitations. Okay. With the present generation, your encoding systems and measuring systems, you can reach approximately 2 to the power 10 usable states, and that's a fraction of the theoretical potential. So that's where the challenge versus things come out. Okay. Google Willow chip is showing that surface codes, they are promising good things, but not very, I will say, being applied by others. Presently, a 50 qubits systems is suboptimal to the, with the present generation 50 qubit system with this capacity, is computational power is lower than the present generation supercomputers available to us. Okay. So that's where we should be there. So present 50 qubit systems, whatever is available, is not crossing the threshold of the supercomputing available today. And we should understand the superconducting computing field is also advancing on day-to-day basis, and better and bigger and better supercomputers are coming every 3 months or so. Okay, next. Now this gives us some idea where the technology is going, and this particular slide maps the all domains of the quantum computing systems, not only limited to IBM or the superconducting side. It is talking about all kind of systems. So just gives you where, let me see where the IBM is there in this. Yeah, so orange one is IBM. Okay. So approximately 50 qubit in 2017, 127 qubit here, and 433 qubit was supposed to come in 22. It only came experimental, not yet launched. This is slightly older slide, and they're supposed to come somewhere. We're focusing on 1000 qubit, but the timeline is not yet clear. Another kind of systems which are called annealers, and that's the field which is again advancing. That's a D-Wave. There's another firm which makes annealer-based quantum systems. They are doing much better, but annealers can even solve a further smaller subset of problem. They are not a generic kind of gate-based quantum computer solve a bigger set of problems. Okay. Google is somewhere around there. They have reached 72 qubits kind of setup. Beyond that, they are also stuck. Okay. So this is where the roadmap should just give a broad idea that which technology is working in what domain. Okay. Next. Okay, so now we have seen these are the challenges of scaling this quantum technology. What are the exact challenges? So we have discussed broadly, but now let's get into what are the actual challenges and how do we solve them. Okay, next. So coming back from that, a very detailed one. This is a much more abstracted information. Okay, so how's the number of qubits working? Okay, so early 2014 we have early error correction. By 2018-20 people started claiming we have a IBM, we have a quantum supremacy. First IBM said, then Google said. Okay, they were expecting that we will reach somewhere around 10 to the power 6 kind of a qubit somewhere around 2030. However, the actual trajectory after 2022-23 is more tapered off, and they're somewhere going into this directions, which talks about probably 2030 or so, we may touch somewhere around 10,000 qubits. Okay. 10,000 qubit tells us, as we saw on the last slide, probably it will give us a 100 qubit logical. So these are a physical qubit. So 10,000, if we reach physical qubits, most likely we will touch the boundary of 100 plus classical qubit. That should start solving the problem which the classical computer or the supercomputers cannot solve. So this is the actual promise. This was the original expectation, desired trajectory. We are not reaching there. So this is a more measured thing. So what we are going to see in next 4 to 5 years, 1,000, 5,000 and 10,000 kind of a qubit processors coming up. Other details, they have the gate fidelity and the volumes are other things, but broadly this. And hopefully 100 qubit plus logical qubits should be derived from that, and that should make a functional system. Okay, next. Okay, now once you are trying to do this, so there are few matrices which need to be kept in mind once you are trying to improve. And actually there's a different set of challenges once you are trying to scale from one stage to other. Okay. In the end, you need that quality. That means what operation you do is reliable. Quantity, number of operations, number of the speed. We need to increase the speed. 15K operations per second is too slow. And connectivity, that you should be able to connect multiple qubits, interaction of qubits, that should be there. And all of them required to be optimized together. So these are the science and engineering challenges of designing the quantum processors. Okay. And if we are looking at the initial 100 to 1,000 qubits, these are the few challenges which comes. Okay. Interconnection bottleneck, real-time latency, decoherence. But as we move from here to the next one, wiring and packaging bottlenecks. That means you have to put the wafer designs challenges starts coming in. Okay. Cryogenic constraints starts coming in, that you need to have a temperature which is consistent across the complete fabric of the wafer. That becomes a challenge. Okay. Electronics becomes too costly because, as I showed earlier, each input requires a microwave tube or the waveguide coming up, which is required to be controlled by a RF generator or RF controller system. Okay, so you have a 10,000 qubit processor. That means now you have 100 lines coming up. You have 10,000 waveguides coming up and going to the systems. You need to have 10,000 amplifiers, 10,000 RF receivers into your microwave stack in the hardware. So those are the electronic challenges. Okay. As you go for even more, then the crosstalk, the number of qubits on the same wafer, they keep getting closer and closer, there will be crosstalk, there will be noise coming in. And so error correction codes which are trying to improve earlier, they will start getting affected. So these are the challenges, and each of these challenges has a this open research field where a lot of work is going on. Interested people will go and go, and you will find all these subsets. There is a research happening, and people are coming up with more and more ideas. Lot of artificial intelligence, machine learning work is going into these domains to make these designs efficient, better, more optimized, less power consuming, lesser noise. So this is a complete open field. where there is a lot of scope of study and future work is there. Next. So as of now, just to give an idea, what is achieved is you are getting a coherence time of around more than 100 microsecond is achieved, and the 2-qubit error rates. That means when the two qubits operate or single gate operation, you will reaching error rate of around 0.1%. But as the scale up happens, okay. So as you go to so this particular site is a number of, so the timeline of your decoherence time, and what's the error probability, the CDF of that. So as your time is increasing, the error probability is also increasing. And the moment you are reaching, say, around 100, say 150, 200, your error probability is almost 0.9. It becomes useless. Okay. So that's another challenge. Similarly, 2-qubit error rates also, as you want to go for better and better systems, again the error probability increases. Okay. So this is the distribution of T1, decoherence time versus the error, and 2-qubit error rate. So once you are trying to improve the error rate down, so both of them are, and if you see both of these, they're kind of correlated. May not be exactly, but so there's another work which is going correlated, or they are representationally, you can make a look, okay, they are correlated, but not exactly the same slope. Slopes are slightly different, but they have a dependency on each other. Next. Okay, so once we go down to the fabrication and you want to put number of qubits onto the wafer, so this represents say 30 centimeter 30 centimeter diameter wafer where the number of qubits have been created. Okay, what it represents is error free. So these qubits, white ones are mostly error free, and the red ones are kind of error prone, and graded setup between them. Now once you are designing from this, you will be making your quantum processors and you'll be doing an interconnect. At this stage, once you want to make a small interconnect, you can identify a small subset within the substrate where most of the qubits are error free or error prone, but to a less extent. But the moment you start designing more and more complex and bigger circuit, you will start realizing more and more qubits which are error prone will start getting into your design. And these are the challenges of semiconductor manufacturing. Semiconductor manufacturing, even if honest, so today if you make 1 million processor, in the end they will actually discard say 10,000 and 15,000 processor because they don't pass the test. So that's how the semiconductor manufacturing works. Similarly, here also you'll have these challenges, but here the challenge is, since you can't discard them, you need to effectively identify and design your routing along with them. So those are the challenges of scaling to a bigger and better processors. But the semiconductor manufacturing process limitations puts a constraint on top of that. Okay. Next. Okay, so this is how the scaling goes. Okay, this is one slide in a nutshell, which tries to know whatever we have understood till now, tries to push everything into one single slide. So let's see what columns represent, then what rows represent, and then we will take a look. So first rows, it talks about, okay, I am just looking at a simple 1 or 2 qubit gates design. Okay. When it goes to the functional side, what they are doing, okay, they are just a gate operation. Physical layout will be few waveguides on a substrate, okay, interacting with each other, Josephine junctions created, and and the Steen code is basically, Steen code is one of the earlier codes where each qubit is connected to 7 other qubits for the error correction. And on top of that, now surface code is applied. So you have a surface code demonstration on that. Okay. Now, once I go for a slightly bigger circuit, that bigger circuit, when represented functionally, these modules will become a subpart of this. These physical layouts will become subparts on this particular chip. Okay. Once we go to fault tolerance quantum information processors, much bigger circuit, more depth. That means this time this logical qubits will become a part of the qubit kind of a setup, and each one becomes, so you have to create multiple of these. These rails where the 20 virtual qubits were there, they have to be connected in a part of a kind of a tree structures. Okay. And here the 2D, you have started a physical layout, 2D lattice. It will become like kind of a very dense environment. And once you need to go for a full scale quantum computing, you want to go, you will have this multiple of these logical qubits coming into this kind of a structure. All these H trees will go fit in that. And finally, you have a quantum classical integration working coming up. So this gives us a challenge, starting from an analog design of a microwave RF oscillator and some Josephine junction created through a semiconductor process, how you reach here. Okay. So these are the challenges of designing at every stage. The manufacturing process has to cater for this. The design process has to cater, has to keep improving. And these are the, in a nutshell, overall view of how a quantum system is going to come up. Okay. Next. Okay, so this is now the last part of the discussion. As I discussed earlier, mostly it's estimated that quantum systems will work in conjunction with the existing high performance computing systems or the data centers or supercomputers. Okay, so that's where the another field of how do I integrate these quantum systems with the high performance computing platforms or the classical platforms. So that's hybrid quantum classical computing. That's the next domain, which is a lot of work is going on. And for going actually scaling up the system to solve real world problems, this is what is needed. Okay. Next. So what this one slide tries to give a full insight into the complete stack, how this stack will work. So you will have at the bottom heterogeneous high performance computing and quantum computing platforms. You will have a CPU, GPUs, and QPUs. Okay. You will have, so this is a heterogeneous platform. You will have some amount of quantum controlling on top of it. You may have a simulator available here also to do some simulation here. Then all that thing will require, say, calibration and do a error mitigation to either reach NISC, which is a immediate target, but in the long run, you need to go to the fault-tolerant quantum computers. So we'll have software stacks, hardware stacks of this, and that's where you will reach to a place where you can do a workload or resource management. If I reach these stages, you can do a workload and resource management. Okay. And then you will have some virtualizer, hypervisor, which will give tools, APIs, and other connectors to work on these platforms. And on top of that, actually the applications will be running. So anybody who is actually accessing a Qiskit platform today, actually you are accessing it here. And I will not say full detailed version of this, but a subset of this, all these layers are already there in the IBM or the Panhellenian platform. So what I'm showing here is not something which is future. It is today, it is happening. Okay. You may not have a HPC programming environment. What they do is a cloud programming environment, but the way they are interfacing is still some high performance computing systems are there through which their quantum computers are interfaced. Okay. So this gives in a nutshell, okay, this is where the future is. There's a lot of scope of study, research, algorithms development in all these layers of future. Okay, next. this is now, once you have to do this kind of a interaction, once we go down to, okay, nutshell, nuts and bolt what I'm doing. Nutshell, there are going to be some QPUs which are need to be interconnected. There will be a quantum controller, okay. There will be some classical systems, AI superchips, GPUs. They will have their own connect. You require to have a low latency data transfer from each of them, okay. It happens, and you need to process the information from classical system in a problem statement converted to the problem statement which can be solved from by the QPUs. Okay, next. Just go to the next one, we'll come back to this. Okay. How that system works? So you'll have a, so I'm just taking example of HP has a Cray programming environment for the your HPC platforms. Okay. Here, you can use either C++ or Python. Classically, using that, we should be able to transfer the problem statement to a synthesis circuit, and it should be able to take it to a quantum circuit, and it should be able to work there. Okay. 2023, if somebody wants to study this in actual implementation, 2023, China has published one paper of compromising approach to the RSA algorithms. Okay, and they have used classical HPC and quantum processors algorithm demonstration. And it's a full published paper. Just say China 2023 HPC super quantum computer algorithm for the cracking RSA 2048. You'll get that idea that how exactly this is. But in the nutshell, this is how the work will happen. You'll take a problem statement, do some solving on the HPC, whatever is not being solved in HPC, and where the quantum computers are good, take that problem there, get the result back, solve the rest of the problem there, and generate the result. Okay, that's the most likely approach on which the future of the quantum is going to be there. And that's where we should be very, very cautious about, conscious about it, cognizant about it. It's not likely to come back in isolation. So if we are trying to be in the quantum computing domain in future, we need to work in conjunction with the HPC platforms. Okay, that's kind of a given. That's how it will happen. Okay, next. Okay, so this is the last slide. What we do, so we are trying to make up our own quantum computing simulator, and we have some estimate that how many number of qubits we will be able to simulate on that. Okay, so our idea is that given a quantum processor, given a particular hardware, if you have got a kind of a simple CPU or 1A100 GPUs, we should be able to simulate, say, around 20 qubits, and simulation times running into a few seconds. Okay, but if you have a much better systems, A16, A100, you should be able to simulate, say, around 35 qubit systems. Okay, so what we talked about the design, what you can do at the back end of the quantum designs. That's what we are trying to do. Few things there. Okay, and that's some numbers which we estimate. It's not our slide. It's a reference slide from outside. I'll give the reference. But these are the few estimates which we have. If we want to run a quantum, if you don't have a quantum computer, but if you want to still run a quantum applications within the organizations, these kind of simulations can be done within the on-premises of the institutes. Okay. Next. Okay. So, sorry, that was this is the last one. So, if I have to take a application, quantum application, develop a quantum application, we first need to know what is the performance gain enabled by the quantum technology or the classical systems. Does my problem fits into the problem which a quantum computer can solve? So there's a list of quantum problems which you can solve. simulations, optimizations, okay, those kind of a thing. Then we should know what are the scientific limits, either by the hardware, error corrections, gate depth, okay, decoherence times, all those things. Okay, then we reached, okay, what are the next devices available, and try to set, can your problem statement, your data set presently can fit in within that space which is permitted today by the available hardware or the simulator to solve. Okay, so that's the approach to uh, kind of identifying problems which can be solved by the quantum systems. Okay, next. Okay, so that's all. So my intention was to give a complete view of the quantum computing technology from the application side to hardware side to the physics side. Okay, so that's what we are talking. Actually, the chip is only this much. The rest of that is our connectors. That's how the quantum computing works. This chip may be around an inch by inch size. That's all, and the rest of it is just your what we talked about, waveguides coming out in and out of it for data input, readouts, and the controllers. Okay. So with that, I have finished. Would like to take any questions if anyone has. So,
traditional communication, take the information and transfer one reverse. Applied to encoder, quantum communication.
yeah, so that Aniket will be covering in detail that how we take the information, okay, and how we actually encode. So there are very multiple techniques of encoding information from classical to quantum domains, and they differ based on the technology, what kind of quantum computer you are using. But generally, for the gate-based quantum computer, he will be covering. Okay, so we'll go into that detail. Okay. Okay, thank you very much. So I finished. Thank you. Yep. Thank you.
Thank you so much, sir. I take this opportunity to sincerely thank our esteemed speaker for delivering such an insightful and thought-provoking session. Sir, your lecture has not only broadened our understanding of this rapidly evolving field, but also inspired us to think about the immense possibilities it holds for the future. It has ignited curiosity and given us a vision of how quantum computing can truly transform industries and even research. We deeply appreciate the time and effort you have taken to share your expertise with us. Thank you once again for accepting our invitation. Thank you, sir. And now I request Professor C.V. Gururao, sir, Professor D. Umadevi, madam, Professor Shivkumar, sir, Professor Fanikishore, sir, to felicitate our esteemed speaker with a small token of gratitude. I also request Professor Jagannadham, sir, of ECE to join the felicitation. Now, the next session is by Mr. Aniket Karia, Quantum Research Engineer, Quantum AI Global, on the topic single qubit and multi-qubit systems, tensor products and states. And now I call upon Mrs. V. Tulasi, madam, to introduce our esteemed speaker.
Let me take the immense pleasure of introducing Mr. Aniket Karia, Quantum Research Engineer, Quantum AI Global. He has done his BTech Computer Science from Birla Institution of Technology and Sciences, Pilani, Goa campus. He has done his Master's from University of Glasgow, UK. He has worked as research engineer in Tata Consultancy Services from September 22 to August 23. He is currently working as quantum research engineer at Quantum AI Global. He is a member of IBM Q Research Group. Let us join our hands to welcome him.
Over there. Hello. 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 Is it working? Okay. No, no, I'll do it. You copied now?
Yes.
The single multi-qubit. Yeah. So today we will start with the basics from single and multi-qubit systems. And I am sorry that my slides may not be as interactive, but I'll try to keep the session interactive so that I know what you guys are grasping. Quantum computing technically is going to be bland text of matrices and qubits and many other things that we'll be looking through over the days. So, right. Okay. Keep scrolling down. So yes, thank you. So these are the contents which we'll try to cover in this session. We'll start off with the motivation for multi-qubit system. We'll recap some on the single qubit system that might have been covered yesterday. Then we'll look at tensor products, density operators, and entanglement to end with. So this would be mainly what we'll be going through. Next, please. Keep scrolling down. Yeah, thank you. Perfect. So as we were discussing the rise of quantum computing, the quantum computing leverages quantum mechanics to process information, which we have been discussing about. So what is this special thing about quantum computing? First thing is superposition. So when we talk about a single qubit, any single qubit gate generally can be written as something like alpha 0 plus beta 1, where alpha and beta are complex values. So this is the real game of superposition, wherein this is actually one single qubit, let's say psi. So the game here is that classically this is 0, classically this is 1, But superposition allows you to take for any alpha, any beta, and make this into one single qubit, which is our actually the powerhouse of where all the, I think someone was asking, how do you represent information? So if you want to represent one single qubit based on the value alpha and beta, your single qubit will look. So this is a general representation. Right. So the true power emerges when multiple qubits are combined. So this is the session where we'll be talking about multi-qubits. So we'll try to see what happens when two qubits combine, how they combine, and what are the operators related to them. Yeah. So there are obviously challenges, but there is opportunities which we want to get to by solving those challenges. So next, please. All right. So there is this dimensionality burden which comes up when we're trying to scale systems. So many quantum applications rely on state preparation. So state preparation is actually preparing your state or qubit into a specific system such that it will solve the problem that we're trying to deal with. And an arbitrary n qubit system requires 2 to the power n real degrees of freedom. So what do I mean by that? I think Kapil sir was already covering something like block sphere. So block sphere actually is a easier way to imagine a 2 qubit system. So here what we do is we have x, y, z axes. And we are actually using this plane wherein we have, technically we have tried to reduce the 2 qubit, which will require 4 dimensions, onto a 3-dimension block sphere. So what I'm trying to make the point here is that for a general n qubit, we require 2 to the power n real degrees of freedom. So what do I mean by that is that we will need that many accesses to represent a n qubit system, just to start off with that. Yeah. So efficient state preparation requires, so the major bottleneck is this exponential scaling, which actually is what quantum computer offers to solve, is that we will try to use qubits and try to process as much information as possible, even though it's exponentially scaled. So for this, there is something like we need efficient state preparation, which exploits something in the order of polynomial size. So instead of going into exponential size, we want to deal with something like polynomial. Next slide. So I'm starting off with the motivation why we are doing, say, multi-qubit, and what are the recent areas wherein they are exploiting multi-qubit. So one of them is tensor networks. So tensor networks is a mathematical framework around which we can solve this problem of exponential scaling. No. Just keep on tensor network. Yep, perfect. Yes. So the idea of tensor network is to decompose a complex quantum states into low-rank tensors connected by virtual bonds. So it's a lot of words here, but the idea I'm trying to make here is that there will be a complex matrix that we can break down. So tensor networks is a solution to break down the complex quantum matrices into low-rank tensors, which are connected by virtual bonds. This will help us significantly reduce the parameters needed to describe the quantum state. Yes. One more, next slide. There is also something like matrix product states, MPS, which is again a promising way to deal with multiple qubits. They're also called tensor trains. So we are talking a lot about tensors here. So they enable efficient amplitude encoding for states with limited entanglement entropy. So again, a few words here. But what I mean by that is that MPS again offers a crucial way to deal with your complex quantum systems. And one thing I would like to point here is MPS avoids issues like barren plateaus. So what is the meaning of barren plateau is like we are all computer science people, we know optimization. So the idea here is that if we have an, say, a optimization graph which looks like this, so the idea is this area would act as a plateau. So you're trying to get out of your plateau to reach, say, a maximum point or whatever, but it might happen that as you increase the dimensionality, your plateaus are becoming longer. So it might happen that you have a well like this, and you are literally stuck at the plateau of it, and you are unable to get out. So MPS would allow to get over that. Yes. And entanglement entropy is bounded by this where, so okay, there is another some entanglement entropy bound which I have given here. But okay, next slide. So MPS will offer efficient encoding, which is the key takeaway I want to give and I'm putting it right at the start of the slide, is tensor networks and MPS. We will not be covering it much more in detail, but I just want to give it out there why multi-qubit systems in today's age, where are they, what are the techniques that they're using. So yes, the efficient encoding and encode functions and structured image data with, say, as I was saying, polynomial depth circuits without ancilla qubits. So what are ancilla qubits? Ancilla qubits are extra qubits which we add for quantum operations. We'll keep hearing these words over the few days. Right. So few examples that are given here, that why MPS is very useful is because even with low degree polynomials, we are able to achieve great accuracies for one, and another one is some chest MNIST image on 14 qubits. So these are the motivation. So next slide. Yeah. So Kapil sir mentioned about something like 50 qubits, 100 qubits, then there are about physical qubits, logical qubits. So actually today we are in the NISQ era, NISQ, which is noisy intermediate scale quantum devices, which actually are noisy. They are small scale, and also that they might not really, like there will be noise, and sometimes it's a probabilistic thing. Sometimes it will give the probability as you need. Sometimes it may not. So the idea is that in today's NISQ era, today, what are the things that we can do best? That's the reason I talked about tensor networks and MPS. So the idea is that we want to reduce the circuit depth, which Kapil sir was also mentioning, that number of gates that you use, so you need to reduce the depth, and as well as make sure that the problems that you're trying to solve are actually matching up. So there is a lot of R&D happening in industry and as well as in academia to find out what problem areas we can solve using this NISQ era capabilities. So right. So I'll just read out this one. Beyond state preparation, tensor networks simulate complex quantum dynamics and solve PDEs. So we are obviously in the domain where we're trying to solve partial differential equations and more. So right. Next. Okay, now coming back to the lighter and easier note. So starting was just an introduction to why and what are the motivating points. So we know classically we have 0 and 1. So we have the definite state 0 and 1, which is the classical bit. And we have operations on it. There are the AND gate, NOR gate, NOT gate to convert, say, 1 to 0 and vice versa. And n-bit system will represent 2 to the power n configuration. So we have, say, 3-bit, then we can represent 0, 0 to 1, 1. So this would represent 8 states. Each of them we keep changing. So yeah, so that is what I mean by that. Next slide. Yeah. And we talk about quantum bits. So quantum bits, it would look like alpha 0 plus beta 1, which is superposition of 0 and 1, right? These are the fundamental units of quantum information. And after you measure, like we keep talking about measurement. So these are the complex probability amplitudes. Once you measure them, so alpha square would represent the probability of getting the 0 state, and a beta square would represent the probability of getting the 1 state. And there is this normalization condition with which we follow strictly, which is alpha square plus beta square will be equal to 1. Right. So this is again laying in the foundation. Next, please. Yeah. So there was the geometric representation which we were talking about. So here you talk about any gate, sorry, any state. Let's say this is the state. So this would be the angle theta, and this on the xy plane where this thing is coming would be, say, angle phi, and this state which is currently strictly on the Bloch sphere. So we are talking about states on the Bloch sphere would be represented by this equation, cos theta by 2 plus e to the power I phi sin theta by 2, 0 and 1. So if you plug in the values, so 0 and 1, if you want to get the state, say 0, which is state 1, so you plug in the values for edge cases, for theta and phi, you will able to get this one. This is the x and y axis again, and z is what we call the computational basis. So we measure in z basis, which is 1 or 0. Okay, sorry, my bad. The north pole is the 0 and south pole is 1. Yeah. Okay. And the states which are inside the Bloch sphere are mixed states. So this is where we will be getting to at, and this is where we'll also be able to see entanglement and more. So right. Yeah. So the angle theta is called the polar, and phi is called the azimuthal angle. And I'm keep giving in keywords so that you guys can check it up also later. Next, please. Yeah. So classically, we combine bits like how we have 00, 000, or 001. And quantum states cannot be described by simple addition or what we call as concatenation of states. So we are trying to concatenate states here to make a bigger system, right? But in quantum computer, what we need is something like tensor product, which combines Hilbert spaces of individual quantum states into composite systems. So Hilbert space is the space which we work in for quantum states because we are first of all having complex amplitudes, and this is just a representation of say a 2-qubit system. And yeah, but yes, the dimensionality of the composite system, the bigger system that we are trying to create, will increase as the product of individual dimensions. So if you are taking a 2-qubit system combining with another 2-qubit system, the dimensionality would be a 4 qubits, 2 into 2. So if you have 2 and 3, it would be 6-qubit the dimension. Next one. Right. Okay. Okay. So just it looks very trivial right now, but we will still just go through it. So our state 0 in matrix form looks like this, and a state 1 would look like this. Now for 2 qubits, we see there is this thing called tensor, which is happening. So how do we write a tensor? Let's say we want to do a tensor between 0 and this. Right. So the process for it is we start off with this 1 and we multiply this over here. So, and there would be this 0, which will multiply by this again. So when we do this, what we'll get is 0, 1. And so which would come down to what?
0, 1.
0, 1, yes. So which is this one. So each of them we can open up and see, but I thought I'll just mention this once. Right. And yes, because if we're talking about 2-qubit system, this would represent our bases in orthonormal basis of a 2-qubit Hilbert state, right? And I already mentioned n-qubit system has 2 to the power n computation basis state. So the idea is that once you keep increasing your basis state itself is 2 to the power n, and the amount of data you can compute is much higher actually. Okay. Next, please. Right. So now we'll just go to a multi-qubit superposition. So if you can just look at the equation for once, it's trying to just bring all the things that we discuss at once. So I'll just try to take an example so that we can see what's happening here. Let's say 001, C001. This X I'm putting as 001. Okay. There is a summation. So I'll just take, say, 2 terms for now, keeping it simple. And X101 and state 101. So the idea here is that this coefficient square summation should be 1. That is a normalization condition. And this would be complex values, and this would be your state 0001 and 1001. So this is actually just a superposition of 3-qubit n equals to 3. So 3-qubit system with just 2 states, and all the 8 states that we know 000 to 1111. Those are the computational basis. Unfortunately, here only the state psi we are talking about has components only in this state and this state. Other all states the values are 0, which you can clearly see. So this is how we represent a general multi-qubit superposition. Again, I have not mentioned anything about entanglement. If you have heard about it, we'll dwell more into it next. So yes, next slide. Okay. So we talked about exponential scaling. We need more complex amplitudes and everything. Yes. So with this said, we talk about, say, high performance computing. Why do we talk about that? Is because such a system scales exponentially, and anything that we want to do, say a classical simulation and all, we need more computing power because we need to do state preparation, and we also need to do information processing of our quantum system. So This is where actually it gets difficult for classical systems to mimic quantum systems, but we can use high performance computing. And the idea is that this would also be where a quantum system will have an advantage, in the sense that we want to make sure that if we only deal with quantum systems, we are able to do much more and much faster. Yeah. Next slide. Right. So now I want to just try to play with some examples so that we know how the qubit system will look like. So I'll just take a rub this off, and if any questions, we can keep having it in middle as well, right? So please do ask, or you can check out this problem and solution which I've also given. And please try to, one thing I've realized, I've trying to learn this field. I would again use the word trying because this field just keeps expanding. There is so much open problems. So one thing I've realized is it's always better to use pen and paper to just see how the qubit states are working out. Okay. So this is the state psi, a 2-qubit system that we are talking about, right? There is something special for this state psi, but I want to keep this a little later when we talk about entanglement. Now let's just take the state psi. And we want to describe the action of X gate. Maybe you would have heard about X gate, which we also call the bit flip gate, and I, which is just the identity gate. So we want to see how a tensor of X and I, which you realize is a 2-qubit, on a 2-qubit state, right? So over here, I've very neatly given what X gate on a single qubit would look like. So this is a very important line over here. So identity won't change the bit, and it will keep it same, and X would just flip it. So I'll still write it down here. So X would flip it. Please pardon my handwriting, but yeah. And we want to check out the operation of this on the state side. So how we go about this is, first thing, we'll just mathematically try to open things up. So we have our state psi, right? So which is the 0, 0, right? And how does this operator look like is, this X would apply on the first qubit of psi. First qubit. This is the first qubit and first qubit. So what I mean is, for state psi, this and this is where your X is actually applying, and a tensor with I means I will apply on this and this. So this what we call is the first qubit and second qubit, right? Right. So I want to open, do that application and try to open it up. Right, as I was saying, X on that, and then I on that, right? And then the signs remain same. X on 1, tensor I on 1, right? I hope you guys can follow this, right? And then we can just simply plug in what X on 0 would look like, what X on 1 would look like. I won't change it, right? So this is actually 1, 0, 0, minus 0, 1. So I'm just writing the final. Okay. Right, 1, 0, minus 0. So if you look at it, this is actually an entangled state, and it transforms this state into another entangled state. I think this could be a good point for me to tell you what an entangled state is. So let us do that. So I hope, you guys can easily follow this. So there is, let's only look at state psi. So there is, I hope this is fine. Any questions for this, or we'll just, okay. So let us just try to break down, what we are actually doing here. So, okay, we have some gates, we have some operations, we can do the math. Everybody is probably good at it. If given the problem, they can do the math. But let's conceptually just break it down. So this is the state psi. Can someone tell me the difference between this state and this state? So this is 0, 0, minus 1, 1, and this is 0, 0, minus 1, 0. If anybody can tell me, what is something special about this or this? First one is entangled. Who was this? Okay. Second one. Oh wow. Thank you so much. So can anybody tell like little more like why is the second one a product state? Right, ma'am. Yes, yes. So if you look at this, this is actually nothing but this state, as you were saying, into our state zero. Right? So we can break this down. We can break this down, but we are unable to break this down into product states. So the idea is this system is entangled and cannot be represented as its subsystem, like in terms of states. There are other ways which we'll look at it. That is where we have density matrix representation. I'll get to that. So yes, perfectly said. So yep, good that this is out of the way. Then we can go ahead. Yeah, next please. Okay. So this is another example which I think we need not solve, but there are some properties which I wanted to mention here. So let's say a tensor product of two operator A cross B satisfies the following properties. So if A and B are Hermitian, A tensor B is also Hermitian. If A and B are projection operators, A tensor B is projection. A and B unitary, A tensor B is unitary. A and B positive, A tensor B positive. So these are some properties, but we'll go to the problem. Next slide. The approach would be same. We'll see the action of say gates. So we'll over the weeks we'll go through gate and their actions. But for now, let's just take it poly Z. We'll change your 0 to 0, but we'll change your 1 to a -1. So it has the phase over here, and X will just flip it. So we are doing the same thing as previously done for the state psi. We'll see the tensor. We'll see the operation of X tensor Z on state psi. So again, X will only act on the first qubits, Z will act on the second qubits, and we'll break down. And this would again changing our initial state to something else. Is this entangled? Is this state entangled?
Yes.
Yes? No? Why no? Again, can we break this down into two, like this is a 2-qubit system. So can we break this down into a product of two states? Actually, we can't break it down. So this is again an entangled system. So again, our operation is just changing, taking us from some entangled state to some another entangled state. Next slide. Yeah. So I mentioned some property. So I was talking about show that if A and B are Hermitian, then A tensor B is Hermitian. So I will just walk through this proof. If anybody has doubts, we can take it up. Yeah. So by definition, Hermitian means A equals to A Hermitian and B equals to B Hermitian. And the adjoint of tensor product of operators is given by tensor products of their adjoint. So this is something which we should take for assumption, granted, right? Then we substitute this over here. We're trying to see if A cross B is Hermitian. And obviously we can see that once we substitute this, we can see that this is nothing but A. This is also like B. So those are Hermitian. But I had to mention this just to let you know that yes, we're talking about this new tensor product. So there are some properties which come with it. So maybe it's a good idea to go through the property I just mentioned in the previous one. So yeah, we can. If any doubts, if no any doubts, we'll just go ahead. Yeah, please. Yeah, next. Yeah. So again, there is another example, right? So I think I might skip this one, just making sure that it's there in the slide. You can again try it out. The same thing I'm trying to ask. Find the resulting state after applying I tensor Y. So your initial I state is applying on the first qubit, Y is applying on the second qubit, and there is this special state phi plus. So I wanted to bring this Bell state word out. So that's the reason this example is there. I will mention about Bell states and more in the entanglement part, right? So you can just go to the next slide and see the result. Okay, back previous, sorry. Yeah, so this is how your state looks like. Again, it's an entangled state. It's not doing much. Correct. Go to the next, yeah. So this is where we'll talk about something which is of more interest when it comes to dealing with bigger systems of quantum computing. So there's something which we call as density operator. So everything that we talked about right now is some state psi, and we mentioned that those are on the block sphere. But there is something which we talk about. Those are called pure states, by the way. Those are pure states. But something which when we talk about mixed states are something which actually end up being inside the block sphere. So we have this block sphere, but they are inside. So what is the significance of it, and how do we get to a state like this, or why is it needed? So we'll get into that. So yeah. Mixed states are classical ensembles of pure states with probabilities. So conceptually, what that means is that if we have some pure state, say, I'll try to take a state phi1 and phi2, but we have an ensemble of these states. So this is some state, say, let's just make it simple, one single qubit. But this is an ensemble, means it is with, say, probability 60, and this is with probability 40. So mixed state would be used to represent this ensemble, which has 60% of the time state, say, psi1, and 40% of the time state psi2. So that is where mixed states are used. And such a subsystem of entangled systems. So this is something which will help us decode when we come across a complicated system. We want to know if it's entangled or not. So we'll go through the subsystem and try to look at operations on it to check if it's actually entangled. So local state within a global entangled system. So we are trying to operate on a, say, larger system which may or may not be entangled. Right. And something like density operator is very useful when we're talking about noise and decoherence. We talked about that qubits today are having noise and they decohere. So the idea is that how do you show these noise? So it will be using the density operator. Right. Yeah. Next slide, please. So there are some definitions to this. So a density operator rho of ensemble of states with some probabilities. This is a probability. So how do I write this one? Rho for this one would look like how? The probability, say this is 0.6, right? Then phi1 plus probability 0.4, phi2. So this we can have more ensemble. This should be 4%, this should be 36%. So we can keep adding depending on how many states or what is the, system that we are dealing with. So I just expanded the definition over here. And yeah, so key properties over here is that it is hermitativity. This rho dagger would be equal to rho. Then there is positive semi-definite. All eigenvalues when you solve for this rho are greater than 0. So that we call as positive semi-definite. And trace equals to 1. So trace is 1. But when we talk trace of rho, but when you talk about trace of rho square, so this would come out as a complicated matrix. So when you take a square of that and try to get the trace of that square matrix, if it's equal to 1, we know that it's a pure state. If it's less than 1, we know it's mixed state. So this is an important thing that we will be using later again. Okay. Next slide. Yeah. So, correct. There is one very simple thing which you can get out of the way. Product state density matrix. So a product state would look like this, right? And the density matrix for it would look like just tensor product of the two individual density matrix. So just try to write it down a bit. So we talked about a density matrix for a mixed state looking like this, combination of their probabilities. But over here, we just know that the whole system is directly represented as a product state. So the density matrix also would just come down as a tensor product for the individual states. But there is something else that's of more concern to us, which helps us describe. Say you have a big system like this I was talking about. But to study more about the system, we want to take partial trace. Please.
Rho A tensor product of rho B
Yes.
with the probabilities. So this is a scalar, right? Probabilities is nothing but your percentage.
Yeah. This is scalar. Perfect.
It's a scalar.
Yeah.
So how does only the thing is 0.6% top the entire matrix, right? So again, it is psi AB is again a matrix.
Yeah.
So scalar product on the matrix. So how is this ensembling
Okay.
effect?
Okay, good question. Actually, to clarify here is that we are talking about product state. So this, in the sense, this is pure states that we're talking about. This is mixed states. When we have mixed states, we are getting them some probability associated, right? So this is where this is a row of mixed state. Can you go back? Yeah. So if you have a row like this, which is a mixed state, your trace of row square is less than 1. But in the pure state, your trace of row square will be 1. But I'm just mentioning the property ones. But the doubt you're trying to ask is, can you? Yeah.
Can you just light on place what is the influence of place?
Okay.
That is the main criteria.
Yeah, perfect. We have one or two examples which probably will help you. If not, we can. Okay. Next one. Yeah. Okay. So let me just try to talk what is partial trace. So we have this system row AB. Now we want to trace. So finding this row A, how do we get it? We trace out B. And to trace out B means there would be elements in this matrix. Let me do. I'll take an example. Let's say row AB. I think we'll come across this example later somewhere, but okay. Okay, this is a row AB, and over here, what are the headings? Headings would be just the 0, 0, 0, 1, 1, 0, 1, 1. Similarly over here, which I'll write down over here, 0, 0, 0, 1, 1, 0, 1, 1. So when we want to, this is the row AB. We want to find row A, which is the density matrix of a subsystem, which is part of this system, row AB. Now to find this, we want to trace out values when, if you look at this J, it is same. So when it says 0, B is 0, both places. So the idea here is B is 0, B is 0 here, B is 0 here, B is 0 here. So this element is of our interest and summing that. So over here, J will be 0 as well as 1. So when J is 1, so this would be the elements. So here, only thing that we're concerned is that when B is same and is say 1, and B is same and is say 0. So I'm not mixing this and this because B values are different. So that is what this equation is actually trying to say. Okay. So this averages out degrees of freedom of subsystem. So the idea is that to get more information about A, we want to trace out the B influence and try to see what row A would look like. Okay. Next slide. Yeah. So now I think we can break down whatever I'm trying to say using examples, right? Yeah. Okay. So I will just read out the question, which says an ensemble of 75% state plus and 25% state minus. So you might have come across these states plus and minus. We'll keep going through this. So plus state and plus and minus state are actually the X and Y axis points on the block sphere for, say, when we had the block sphere, we had X, Y, Z. So Z is computationally 0 and 1. Z is that. X is our state plus and minus, which are the pole opposites on the block sphere for X axis. And Y would have something like plus I and minus I. I'm not defining them, but okay. So we are talking about and mixed state, obviously, because we are taking ensemble of two pure states with probability mixture. Write the density operator, yes, and determine if it's pure or mixed by calculating this. So can we have a guess on the last part? If it would be pure or mixed by calculating trace of row square? Like, can we guess if it should be
PR of rho square is greater than or equal to?
Yeah, if it's equal to 1, pure. Yeah, less than 1, mixed. So we can guess that it should be mixed because we are already starting with a mixer state. Okay, but I want to break this down so we just know how a density operator would look like. So to find this rho, we will go back to the definition which said that there was probability. First one is plus, so we'll write down as like this, plus 1/4 minus. Again, pardon my handwriting, but yeah. So that's the first line. Once we open this up, I will try to write down more in detail over here. So your plus state is what? 0 plus 1, right? 1/√2. This would be 0 plus 1. 1/√2 will go to 1/√2. This will become 1/2. Just multiplying it. Okay, this whole thing 3/4 plus 1/4, 1/2 minus. Minus state. Minus state is nothing but your 0 minus 1, 0 minus 1. So this on this. Do you understand the operation like this? Huh? Not okay. Okay. I'll break it. Actually, then let's do one thing. I have one more. Can you open up that PDF? I hope I have more details in it. हाँ, oh, इसीलिए sir. Open the folder. Yeah. Can you open the lecture notes? Yeah. Yeah. Lecture notes. Yeah. Yeah. So in the PPT, I was able to only add some aspects. There are other more details which will help you in the lecture notes. We'll go to the example we are discussing. Can you go down? I'll tell you. Wait. Oh, yeah. This one. Just click on that, page 16. Below 16. Yeah, click on that. Yeah. Yeah. Okay. Can you zoom in? Yeah, zoom in, please. Over here. Yeah, perfect. Yeah. Just scroll down. Yep. That's it. So, when we talk about, say, state 1, keep that only. Lecture slide, please. Thank you. Yep. So when we talk about this state, I said this is something like 0, 1. When we talk about 0, I said this is something like 1, 0. So this is actually the ket notion of it. Yep. And the bra, can you tell me? That would row vector. That would be 1, 0 or 0, 1? 1, 0. Okay, so this is where we will try to see the actions of these individual components. So I was trying to write down plus with plus. So plus would look like this. Sorry? Yeah, outer product and inner product. Perfect. So when we have the inner product, we call the bracket. So when we have something like, say, plus with, sorry. This is the inner product. So this is actually that's how I remember also. This is your bra. This is your ket. So these are your ket. These are your bras. And here actually we are having some outer product, not inner product. This is inner product. Outer product would be this, would be out. So we're trying to write and break down the outer products over here. Okay. Okay. So your plus state action would bring us to this. So we have outer product 0, 0, 0, 1, 1, 0. Okay. And same for the minus state. Now, these are the things which we are a little comfortable working with. So we will plug this 2 into our row. Can you scroll down a bit? Yep, perfect. That's it. That's it. That's it. So all the math once work out like 3 by 4, 1 by 2. This, it will eventually lead us to this. I'll write this down at least. That would be 1 by 2. Okay, 1 by 4, 0, 1, 1 by 4, 1, 0, and 1 by 2, 1, 1. So how do we write this in the matrix form? Is just a simple, yeah. 1 by 2, 0, 1 will be over here, 1, 0 will be over here. Yeah. Okay. Correct. So this is how our system, which we of interest was, you know, a 75% mixture of plus and 25% mixture of minus. My only question here is this matrix dimensionality as we expect? Like, is it right? Yes, it is right, because we are actually only dealing with single qubit states. This is like, might look like, okay, plus is some 0 plus 1, but it is just 0 plus 1. There is no second qubit coming in. So there is just 2 into 2 matrix that we have. And this is actually if you try to visualize this on a block sphere, you will fall into the block sphere. You won't be outside the block sphere. So this is where we know that this is actually a mixed state. And to mathematically just know that we've calculated the trace of rho square. What does that mean is, we have this rho, you multiply it with itself, which is rho, then you have rho square, you trace it out. So this is your rho square, you trace it out, so you get 5 by 8, which is actually less than 1. So we know that this is a mixed system and not a pure state. Yeah. Let's go back to the the PPT. So I hope I can share these things with you, so you guys can also have a look at it in your leisure time. Right, next. Yeah. Okay. So we saw that for a mixed state. Let us see that for a product state. Okay. So, okay, this is the question. We'll go back to the lecture notes again. Just simplify the calculations in there. Scroll down. Yeah, perfect. Okay. Right. So now we have the state, yeah, perfect. State A and B. Okay. And we want to find rho A, rho B, and find the reduced density operator. So in finding the reduced density operator, we'll come across the partial trace and other things. Yeah. So we know for a product state, one very, good point we know is that for a product state, rho AB would be rho A tensor rho B, right? So in this, things get simple is that we directly calculate rho A, which would, I'll just write down the main formulas so you guys can again fill it up with other states. Okay, so your rho A is nothing but state A, state B. Rho B is same, but for the state B. And one good idea is that we know these two are product states, so we know rho AB would be rho A tensor rho B. So this is the math that we are doing here. It looks a bit complicated, but we can break it down. So your rho A looks like 1 by 2, 1 iota minus iota 1. And this rho B looks like 1 by 3, 2 root 2 root 2 1. Right. So can you scroll down? So your row AB would just nothing be a tensor. So again, to recollect what the tensor would be, we'll take the first element, we'll apply the whole matrix, perfect. Then we'll take the second element, third element, fourth element, and we'll try to compute. This is where we'll get the row AB. I'm sorry we can't see this completely, but the idea here is that this row AB, oh yeah, we can see most of it. Okay. So the idea here is that this row AB can be easily calculated by a row tensor row B. So this is again bringing back the tensors that we were talking about before, right? Go down, please. That's it. This points, yeah. Yeah. So now to find row A, we can perform partial trace over row AB. And idea is actually when you try to trace out row AB, you will end up getting. One second. Yeah. Trace out B over this would give you row A trace row B. So this is a very simple formula that can be used for product states. The idea is that anything we are trying to trace out, say trace out B on row AB, but row AB we know is a tensor of row A into row B. So this would actually come out because there is nothing in row A of tracing out from B. So there is no influence of B on this one. So this we can easily get out, and that would turn out to be trace of row B. Okay. So this is how we would get, what would this be? This would be a tracing out B, so that would give us row A. And trace of row B is always 1 actually. And this we know why is the case, because that's a product state. So trace of row B will become 1. This is a very simple equation, but for the entangled system is where we will see how it varies and how it's going to like make a difference. So let's scroll down to the entangled system. Yep. Yep. Thank you. So again, we have a mixture of state 75% plus, 25% minus. And we want to write down the density operator, determine if it's pure or this. Let's scroll down. I think we have seen the math for some of this. Yeah. Let's scroll down. Wait. Just, okay, over here. I just written down that row O before that. So this is what row we'll get after the ensemble of say 75% plus and 25% minus. And after this row, we calculate the row square and we saw that it's less than 1. That was the idea. Scroll down again. 1 second now. Okay, can you go back to the slides just to make sure which example? Yeah. Okay, next. Okay, just before this. 6.3 before. Yeah, that's it. Okay, we'll look at this one then. Okay, yeah. So assume that we share a entangled state between Alice and Bob. So we all know that okay, there is something special about this entangled state, right? We are keep mentioning it. So this state plus 5 plus will look like this. So these are some Bell states that we call for our ease, right? Okay. So what does that mean? Like I'll just try to break it down. What that means is, like say Alice is the first qubit Alice has, and Bob has the second qubit. So let's say Alice is on Earth, Bob likes to be in the space, so she is in the moon. So yeah, so what entangled state means is that say Alice performs a measurement on Earth, and it found that its qubit is say 0. Bob has no idea about it, they're not communicating, nothing. But if they are from a resource which is entangled, which is our state, say 5 plus, the idea over here is that instantly Bob's state is going to be 0 or 1. Can we guess? This depends on the share that like what we are sharing. So this is the 5 plus state we are sharing. So can we tell if Alice measures Bob, what would be, if Alice measures 0, what would be for Bob? Why? Because, yeah, 0 plus 0. If this state was something like 0, 1 plus say, 0, 1, say minus 1, 0, 0, 1, minus 1, 0, then this 0 and 1 is the way they are correlated. Over here, the correlation is, over here the correlation is 0 to 0. And let's say Alice measured and got 1. So we know for sure that Bob also will have 1. And this is actually very debatable, that how is this information being traveled faster than speed of light. So there are a lot of open questions in this entanglement only, but we know that entanglement has been proved and it's already been verified in lab. So right, so this is the crazy thing about quantum computing. One was superposition and a second one is entanglement. Okay, so we'll just go back to the problem. So verify its purity, trace. Main thing that I want to show you is row of A. Okay. So this is row AB would look like this. I will not write down this again, assuming that we can calculate this through. Then trace of row square AB comes out to be 1. So what does that mean? It means that this system represents something like a pure state. But when we try to find row A, this is where things will get interesting. We'll try to find the reduced subsystem only on A. Next slide, yeah. Okay. Show me the first one, sorry. I'll just write this down, yeah. So I think I had already shown this 1 0 0 1 0 0 0 0 0 0 0 0 1 0 0 1. Okay. To find this is row AB. How do we find row A? Next one, yeah. So row AB would be tracing out B. So how do you trace out? Say when B is 0. We talked about it, right? So when B is 0, this is the matrix that it looks like over there. And when B is 1, this is the. So what we're doing is we're trying to add it. Okay. And this is how your row A would look like. Sorry? Just last and few entanglement, yeah. Yeah, no, I understand. So the point here is that once you calculate it, you get row A as this. And once you find the purity of row A, which is trace of row A square, which is the subsystem, you find that this is less than 1. And this is the hallmark of something which we talk about entanglement. So the idea is that row A is maximally mixed state. That's the reason mixed state is one thing, but maximally mixed is that it is as maximally mixed means 50-50%, you can say. But the idea is that more mixed it is, the more entangled the state is. So the highest possible entanglement is there in something like Bell state, and that is where we called the reduced operator would look like a maximally mixed state, and this is where we can see that the subsystems individually are uncertain. So from this subsystem, after getting this, row A, we can't say anything about A actually. We can't say what's happening with A. So this is what it means. That's why we called it as maximally mixed. So we can't say any property from A. But having found that, we can conclude that it is coming from an entangled system row AB. So row AB is entangled and it should be understood as an entangled system and not like product state, because it cannot be split. We can see that when we're trying to find the trace of, we're trying to find the row A, we are unable to get any more information. This is maximally mixed state. Yeah. Next, please. Right. Again, this one proved that for a mixed state, trace of row square is less than 1. This is a very simple, we are been using this, but I'm not going to this proof. Proof is a little lengthy. You can go through again. Lecture notes are there. Next slide. Yeah. Next slide. Yeah. So understanding entanglement. I was talking a bit about this in middle of the lecture itself, so that we know what we're talking about. And when I'm again taking the state 5+, we're taking some other entangled state. What's happening? Is just something that written down in maths, or is there some conceptual thing? So the conceptual thing is this only, that it's a unique quantum phenomena where particles are intrinsically linked. Even though one is at moon, one is at earth, they are intrinsically linked. The states cannot be described independently of others regardless of this distance. So even if they are infinite distance apart, they cannot be described without like each other, or they can only be described as a whole system. This is something which Einstein called as a spooky action at a distance, and he really didn't like it. He felt that there was something wrong with this quantum thing, or there's something wrong with entanglement, but that's not the case. It does happen, and this is the fundamental resource that we use for quantum communication and computation, and we'll be going through that in more detail over the days. Next slide. Yeah, so these are the 4 special states: phi plus, phi minus, psi plus, psi minus. These we just call as Bell states, and these are the so-called Bell states that we call it, 4 states. Right, next slide. Yeah, so I think I will end with this. So this is something which will also help you with the next class, which is going to be coming up on gates and other, quantum phenomena. So the idea is we talk about this state, phi plus, but how do we create it? So let's go back to something basic, which we will be seeing it throughout. So this is, say, qubit A, qubit B. We apply Hadamard on first qubit, and there is something like C0 gate, which is a control knot. So only when this control qubit is 1, it flips the state of B. When it's 0, it does nothing. So this is how we would generate this state phi plus using this circuit. So assuming this, we start with 0, B is also 0. We add a Hadamard gate, then we add a C0 gate, and this is where we will get phi plus. How do we get the other states? We repeat the same thing, but idea is either we can start with different of this, but I will start with 0 itself, A equals to 0, B equals to 0, and say you want the state phi minus. So here you will add the Z gate, Z gate, and this would look like phi minus. So this Z gate changes your state. So after this, if I add a Z gate, it will become phi minus. After this, if I add a X gate, after this, it becomes a phi plus. And if we add both X and Z, it becomes a phi minus. Maybe we'll look at this more in detail, but the idea is just simply this: a Hadamard and a C0 creates entanglement. So this is phi plus. If you just know for one state, we are good enough. Next, I think we are almost done. Yeah, I'll just mention the properties. So non-locality correlation exists regardless of spatial separation. That's why I wanted to get the Earth Moon example. Then there is something like Bell's theorem confirms quantum predictions cannot be explained by local hidden variable theories. This is again a very deep discussion that happened in early times. What is something like local hidden variable theory? So the idea was that we computer scientists were trying to say that, oh, you guys don't know much about the system. There is something local and hidden variable which we are not aware of. That's why there is something like entanglement that we are seeing. But that's actually not the case. We have that cannot be explained, and we have proof that any local hidden variable theory cannot explain quantum, this weirdness or entanglement. And yes, fragility, sensitive to environmental interactions, decoherence, again a keyword, and resource for quantum technology, crucial for teleportation, superdense coding, cryptography, quantum algorithms. So we hope to give you more insights into all of these things, teleportation, superdense cryptography, and quantum algorithms. But I hope this it's a precursor to more detailed concepts. Next, please. I think we should be done here. Next. Okay, quantum advantage source. Okay, next slide. We'll just complete it. Yeah, we are done here. Thank you so much. And if there are any questions, you may ask, or we can always discuss later. But
any questions?
Okay. Thank you so much for paying attention. I hope we all are hungry and we'll get to lunch soon. Thank you.
Thank you so much, sir.
Thank you.
Thank you for sparing your valuable time and enriching our knowledge. And now I request Professor C.V. Guru Rao, sir, Professor Y. Anuradha, madam, to Professor D. Umadevi, madam, to felicitate our speaker with a small token of gratitude. And also Professor Fanikishore, sir, and Professor Jagannadham, sir, to join them.
Please take your seat.
Yes, sir.
So sorry.
Thank you. Thank you, sir. Thank you. Thank you, sir. Thank you, ma'am. Thank you. Thank you. Glad to be here and contribute. Yeah, I'll be around. Thank you so much. Thank you, sir. Thank you.
Now lunch break in the DC and 2 o'clock sharp.
Thank you, ma'am.
Kindly adjust the class and come with laptops. So that in the afternoon it is hands-on session.
Yeah, yeah. Yes.